Be welcome, everyone. Thank you for joining us today. Our webinar is about how Stiction disrupts PID control and what to do about it. And just before we start, feel free to input your questions and comments on the control panel here in GoToWebinar. There is a tab named Questions, and in the end of this webinar, George and Damien will be answering some of that. Our today presenters are Damien Moreau and George Buckley. Damien is our EMEA Integration Director at Control Station, with over 20 years of industrial experience, specializing in process control diagnostics and optimization with many manufacturers, and leveraging technical and engineering positions across key industries. And George is a president of Sage Feedback. He's a leader in process control industry, focusing his career on enhancing plant operations and advancing control systems. For those who are new to Control Station, we've been an active innovator since the 80s. Today, we are proud to support an increasingly global clientele, and our customers include leading manufacturers from across the process industries.
Thanks, Vera. Welcome all to this webinar. Just a quick walk through the agenda there. We see there's kind of three main headers. Really what we want to do is practically talk about Stiction and how to understand it, how to see it happen, and then what you want to do about it, and the effects of increasing Stiction on your process. We have a couple of case studies in here to talk through examples, etc., and using software and indeed just manual methods to try and get you some tools to use to understand does your process have Stiction and what you can do about it. Thanks, Vera. We go to the next slide. Okay, so here's a survey question just to start off. Please just read through and pick your best response. What do you know about Stiction? Do you use it? Do you monitor for it? Is it an irregular thing, or you have a program in place to actively and proactively go after it? Perhaps part of your maintenance program. But just take a minute there or so just to make some selections. George, where do you think these numbers are? The statistics are going to go? I can guess where we're going to be, in middle of the road there somewhere, I suppose. But you never know. It'll be interesting to see what. I
would think so. I mean, we'll see. But I think right, if folks are coming to a webinar about Stiction, you want to learn more. It's a good place to do that. So I think we'll have a mix of folks here. Has been quite rare, but becoming a little more prevalent for folks to have active programs in place to monitor and systematically manage Stiction. So I hope to see that number as we do these webinars over time trending upwards, because it is a critical part of control performance, as we'll see in the webinar.
Absolutely. I think the awareness of that data is okay. So as we guessed, the 1368. So the majority of people in that know what it is, but don't actively manage it. That's not unusual, I suppose.
I would say that's quite typical, right? People are aware of it. They know it's a problem. It's out there, but what to do about it with all the other priorities you have on your plate at the plant? How much time should you put into looking after Stiction versus all the other squeaky wheels, as it were, that are out there that you have to go chase down and deal with on a daily basis.
Yeah, hopefully we can get you, some of you, to go into that actively monitoring, I suppose, because that's something that will certainly feed into your preventative maintenances and those kind of things.
Right. I think after today's webinar, maybe we'll at least raise the awareness a little more about what can be done there to try to actively manage Stiction without necessarily having it be a big drag on your time. That's really what we're after. So let's start here with a brief definition of Stiction and what it is. Generally, it's been said to come from kind of a mash of words together. Some have said it's static plus friction. I've heard some say that it's stick plus friction merged together to make this kind of made up word, stiction. And really what it ultimately means is it's the tendency of a valve to resist movement until kind of repeated pressure has been placed on the valve to make that valve move. So you have a valve at one certain position to start with. The controller is calling for, let's say, the valve to open more and more and more, but the pressure against the valve is not enough to overcome that stiction. And so it takes a little bit more pressure to build up, and then suddenly the valve will pop and move to a new location. I used to teach this as the tendency like when you are trying to reposition a refrigerator on a sticky floor, right? You kind of put your shoulder against it and you push and push and push that refrigerator and nothing happens, and then suddenly the refrigerator slides a couple of inches
on the grease, yes,
too far. Then you've got to get on the other side of the refrigerator and push it back. But that stick and friction phenomenon happens all the time in control valves, and that is what we will refer to as stiction throughout this webinar.
Yeah, I like to call it sticky friction. That's just that it kind of rolls off the tongue a bit better as the definition for it. You know, the presumption is all of your valves and all of your systems are working perfectly. You know, but it's over time that this is where it starts to come into the process. And in reality, it's things that you were doing or didn't do from day one of your process. You know, you weren't doing maintenance, you were too aggressively controlling your processes, you were, you know, there's lots of reasons why stiction can start to show up into a system. And it's something that you need to keep an eye out for, particularly in perhaps the 3 to 5 year cycle on your processes. If you're not doing proactive maintenance, that's when it's really going to start to bite. And next slide there, please.
Right, I should point out just briefly that this, while we'll talk mostly about control valves here, this can also affect other actuators in a plant as well. So dampers, other types of devices.
Yeah. Guide vanes, there's lots of them out there that have the resistance to change. I suppose if it is what it, you know, quite clearly motors and pumps won't have it, but you know, it's anything else that has resistance to change, very much so. You know, so how does it exhibit itself, I suppose, is what this slide is all about. You know, it's got that sticky stem. It's the actuator has a reluctance to move. The static friction is holding the stem in that position. The packing is probably a little drier, maybe it's a little tight because it's hot or dry, etc. And it's preventing the actuator to move. So the pneumatics have to keep incrementing onto that to get the movement. Our PID is going to ask for change. If the process is in error, it's going to start integrating that error and it's going to start to accumulate value. As the valve output signal changes, it doesn't necessarily mean that the valve is actually changing. It's just the 4 to 20 milliamp going out, and it's going to integrate with the PID output, but nothing happens. And we see on the lower track there that the output of the signal is starting to work its way up in very small increments, but nothing is happening in our process until we've moved a little over 1% of the valve before we see any action on the process variable. You know, and that's an indication that the valve is stuck. Now there can be a degree of hysteresis or valve lash or linkage looseness play in that can cause some of that. You know, and ideally to accurately detect it, you need to actuate the valve in a number of in equal and opposite directions, I suppose, to clearly define the amount and the distance of it. George?
That's right. I mean, sometimes you can have a little bit of looseness in the valve, so you have to, let's say, actuate the valve before you see any movement at all. But once you've done that, now you try to move it again, and it's not moving. This is clearly stiction. And as you'll see, it kind of nothing happens, and then all of a sudden, pop, it moves to make up the difference and sometimes more for what you've been trying to do with it all along here as the pressure has been building, as that interval action on the controller has been trying to get it to move.
One of the tests I've done on more than one occasion is put my finger on the stem, you know, and request for a percentage change. And you know, not every valve is accessible, not every valve is viewable on the stem, but if the opportunity is there, it certainly gives you that instant feedback that there's no action on it.
Good.
So sorry, Vera, I should have said, get you to send it on. The result of this lack of performance, you know, what's it going to do to your processes? Well, it's probably going to do a little bit or all of every one of those, you know, production throughput, production yield, energy consumption, production defects. Now, if we think of those collectively, what's the likely cause or the result of stiction? Stiction is going to start to stop the valve responding efficiently or on demand, which is going to start putting oscillation in your process. Effectively, Stiction's net result is oscillation either in that process or potentially even a downstream process. And that's where the performance starts to decay. Oscillation is average absolute error increase. Oscillation is moving away from set point. Oscillation is variation in where you want to have stable control. And it's going to feed into all of those actions there to start to bring variability into it. You know, throughput, if you can't reach set point quickly, you're going to reduce your throughput. Yield, if you're not at your perfect set points and your good temperatures for chemical conversions, you're going to reduce your yield. Consumption, constantly switching back and forward, although there's not a huge waste of energy because it'll be a too much too little scenario, there is going to be a draw on the systems that they never get stable, and it probably runs to a 2.25 boilers running, or you know, there's an increased floating reserve in some of those. And defects, you know, again, that's from that poor set point management, you know, variability causing not perfect product being produced.
You know, with this popping movement of the valve up and down and up and down, it's highly unlikely that the valve is ever going to settle at exactly the right place to hold set point. And we all know that, I mean, the degrees of efficiency you get by getting closer to set point, you know, matter significantly. So if you have a valve that has, let's say, 1% stiction, and maybe that valve is only 20% open, right? If the valve is 20% open, but it has 1% stiction, that means it's going, you know, from 19 to 21, which is quite a swing on that valve, right? Quite a swing on a valve that's 20% open. It could mean that your production is going up or down 5%, right? Or your energy consumption is going up or down 5%, just on 1% stiction at a valve that's 20% open. So the fact that you're not landing right on set point is also critical here to the effect of controls. And we'll see more on that in some of the later slides.
Yep.
So here we start to see a little bit about, well, where does it come from? Where does stiction come from? You've heard Damien refer to a few places so far in the early on setup and operation of the plant. Certainly, we see problems with stiction that come from wear on the seats. If you've got wear, or particularly a rough spot on the seat of a valve, it can hang up and cause some stiction and not move. And I've seen cases where, you know, you take a valve apart on the shutdown and you discover, hey, the valve seat was just all torn to pieces, and no wonder that you had huge amounts of stiction on the valve. It can be lubrication, and as Damien referred to before, valve packing is a really significant cause of stiction in valves, especially in these days of dealing with fugitive emissions requirements. So, you know, what do people do when you have a significant amount of fugitive emissions, but go out to the valve and tighten down on the packing a bit, try to compress it a bit and prevent leakage from coming out the valve stem. Well, what that does is just makes it harder and harder for that valve stem to move because the packing is held so tight. You can have issues with the actuator itself. I'll get to that more in the sizing and selection piece, but the environment and operational conditions can also have a significant impact here, particularly the fluid going through the valve. If it's particularly corrosive or sticky, those kind of fluids can have a significant impact on the performance of the valve, and also depending upon the type of valve that you have. If you have a globe valve, a little less resistant or affected by some of those kind of things, but other types of valve, ball valves and so on, may be more susceptible to certain types of stiction going through, and corrosion as well. The actuator is critically important to this. And when we say sizing and selection, the sizing and selection of the valve, yes, but I would say even more especially the sizing and selection of the actuator that is on the valve. I've seen situations where the actuator is just woefully undersized, just not able to move the valve. I've seen situations where the actuator is perfectly sized, maybe even too big for the job, but the air supply feeding that actuator it just wasn't big enough to bring enough volume to the actuator to actually have it effectively move the valve as much as was needed, as quickly as was needed. So that led to a cause of stiction. I've seen situations where you might even have the right air supply and the right actuator, but maybe the wrong size spring in the actuator, as those are adjustable and replaceable. So many different ways that the mechanical action on this valve can lead to stiction, right? Valves are very mechanical devices, as are dampers, and there are many, many places here for binding and stiction to creep in and cause this effect that we refer to collectively as stiction.
It's interesting you mentioned binding and stiction. Like that image there is of a valve with a positioner, but it's not immune to stiction effects as well. The positioner is going to try and adapt to it, but again, it has to overcome all of that stiction, which can cause the oscillation even more so. So it's if for our audience, just because you have a positioner type setup on your valves doesn't mean you're immune to stiction.
Right. In fact, the positioner itself can cause the valve to go into that cycle if the rest of the valve has some stiction on it. Right. Great. Now we can go on to the next slide here. Right. So there have been a number of studies published over the years that look at different forms of issues. This number here, about 35% of valves in the field known to have issues, is pretty typical. I've seen anywhere 30 to 40% kind of numbers for valves that have significant issues. Now this is kind of a lumped summary of all the types of valve problems that a valve might have. Might be that the travel's not set properly, or the actuator is not proper, or the bench set for where the valve is open and closed maybe not set properly. But friction and stiction is definitely one of those things that contributes to some 30% of valves with significant issues. And the number of valves in your plant that are subject to stiction, or the percentage of valves in your plant that are subject to stiction, subject to many different things, types of fluids and when your plant was designed and all of those kind of things. But also, very importantly, whether or not you have a program to look at to evaluate stiction in your plant. Because if you don't have a program at all, if you don't have any kind of organized approach to looking for stiction, chances are it's there and it's just going undetected and creating these problems in the field for your valves, and you just don't even know about it. It's like having a problem that you don't even know about in your plant, and that can be quite dangerous, because quite often, and you'll see on some of the coming slides, stiction can be a driving force that's causing all manner of other problems to occur throughout your plant as it creates this oscillation that propagates.
Absolutely. It's trying to differentiate between those undersized, oversized, incorrect travels, so that you're diagnosing them like as early as possible to find out the causes. It's very hard to change an oversized or an undersized valve. It's not something you just whip one out and put a new valve in. You may have to live with it, but understanding what it's doing, understanding the limitations will then feed into that. undersize and oversize can also feed into stiction. By overuse and underuse of valves can cause the same the stiction issues to increase on it. So it's defining each valve's performance and then getting a program to manage that until you can get to a shutdown, or until you're upsizing your plant next year and you can use that opportunity as a time to put in the more appropriate system there for it. You know, it's going to be key to it. Next slide there, please, Vera. Just a sojourn away from our discussion on Stiction, just to let you know, this program of webinars is all about practical applications. We're looking at specific topics across this, so I would invite you to book your calendar for our next one, which is going to be on level control, surge tanks, and standpipes. Maxim Lachance is a project manager for BBA. He's an in-depth user of tuning and monitoring solutions, and is an expert in this field. So I would definitely recommend that you mark your calendars for this one. And Vera, next slide, please. See another survey question here, just to keep you involved and interacted with it. Again, you know, how much is acceptable? Now, we've talked about it and we said Stiction is there, but what do you think is, you know, what can we live with? What do you live with on your plant? What are the likely numbers? What one of those do you think is acceptable, appropriate? Who cares? You know, etc. Suppose no amount of stiction is acceptable. That's probably too strong a statement, but you know, it's no amount of unmeasured stiction is acceptable, perhaps.
Yeah, and I have actually seen plants try to implement something that says no amount of stiction is acceptable, and implement a program for that, and it's quite difficult to hold yourself to a standard that high.
Yeah.
Quite difficult.
Yeah, let me close the pool and share the results here.
Okay, that's again, nobody said none, which is there's always going to be, we live and operate in the real world, you know, so it's the split between the small amount and modest is probably a fair amount. George?
Yeah, it depends is almost always my favorite answer to any question, because there are always special cases, right? But absolutely, for critical loops in your plant, you want to get as close to zero as possible. For loops that you know are really important in the production, in the quality, in the energy consumption of your plant, for those critical loops, the fuel flows, the key quality impacting loops, you want to get that stiction down to as close to zero as possible, because as you'll see in the coming slides, it has a significant impact on the performance of the control loop as a whole. For the loops that are not critically important, you know, I like to think that, well, I'll say this, you can simplify your life quite a bit if you establish a standard for the plant and say that, okay, for non-critical control loops, you know, anything more than 1% requires action, or something along those lines, because then you won't have to have an argument and a debate every single time that somebody discovers stiction on a valve. You can establish a standard for your maintenance practices that says, for a non-critical loop, if it has more than 1% of maintenance or something like that, then that means we will add it to the list for maintenance, for shutdown work, and so on.
Not going to cause a problem, George, but I suppose it's you're being proactive about your process. You know, at 1% stiction, you've lost 1% control of your process. You know, so on a 0 to 100 instrument, you've technically lost about 1 degree of control. Now, if your process needs to be tighter than that, you know, that's the measurement of it. You know, so it's percentage stiction is the loss of control, I suppose. So it's that proactive measurement. you know, is
Or,
what
you know, and if you decide your plant isn't quite as sensitive to that precise level of control, maybe you can set it at 2% and say, well, if anything has more than 2% stiction, then we definitely are going to take action. But my point is, try to fight that battle up front and establish a practice for your plant so you don't have to fight the battle on every single valve that comes along, because you're always going to have one group that wants to fix the valve and another group that doesn't want to add the extra work. Right.
Defining the rate of change of that is going to be key to how quickly you need to address it, you know, is the thing when you start to cause problems.
Yep, yeah, and especially if you have a, you know, lengthy time between turnarounds. If it's 3 years between turnarounds, you've got to make a lot of decisions that are going to have an impact on the following 3 years if you don't do something now.
I was thinking about that earlier, actually, that, you know, batch type systems, you can get in, get it, you can do a maintenance, but on those 2-year turnaround sites, they're something that needs, you know, to plan those actions in, you know, and maybe you need to live with that degree of stiction, and we can, you know, to over that time, you know, but
it can be. So now we're going to start switching a little bit of our focus here to how would we know if we had stiction. You know, here are a number of trends from the valves in a plant. The control outputs on the top trend, and their PV trends in the bottom here. And looking at these, you can see a lot of movement, some long-term cycling, some short-term cycling, and the question is, do we have stiction here? And the answer is it's quite hard to tell from just looking at this. It's easy to confuse stiction with oscillations due to tuning or oscillations due to other process issues. It's quite difficult to look at these charts at this level and say for sure where you have stiction and how much stiction you have. And also keep in mind that because stiction is this kind of mechanical beast of a problem, it can be very irregular. It may only happen when the valve is in certain regions and not happen when the valve is in other regions. It may only happen when your air supply pressure drops by a little bit. It may only happen when the process fluid is a little bit thicker or a little bit cooler or a little bit stickier. Like, it may only happen in these kind of irregular situations. And so it can be very difficult just using the naked eye to look at a set of trends and try to figure out, is there stiction here or not? You know, how would I know?
yeah, it's absolutely, it's you can understand your process is oscillating, but why is it oscillating? You can see, I see our PVs are moving around, but you know, which ones are problems, which ones are tuning, etc. It's going to lead you down a number of garden paths until you kind of diagnose it. You need tools to be able to give you a kind of a point of focus, I suppose.
Right.
Next slide there, please, Vera. So again, we're just going to show you how Plant ESP kind of can display stiction, perhaps is the best way to do it. There's our Plant ESP demo site there. You can see I've highlighted the table view there. So Vera, just select the table view there, and it drills into, like, you're looking at all of the loops in this particular unit and all of the details, but I draw your attention to that yellow column over to the right hand side. It's the stiction amount column. So this is like we said, tracking stiction over time will give you this information to start making decisions on it. And you can see from the very bottom of that column to the top, you know, there's very small amounts to starting to get significant amount. I'm just going to select FIC 406 there, just as an example, to drill in and show you what the process will show you from a stiction point of view. We see here the trend across the top is there's two trends there. There's a likelihood and an amount. So what the mathematics can do that the human eye isn't going to be able to do to those oscillating trends is look for stiction events. Look for when the valve didn't move. Now, we don't get feedback from our valves, but we're looking for PV response. We ask the output to change. Did the PV change accordingly. And that's the way in which we start to look for it. Because it's not a direct linkage feedback type system, it's a likelihood, it's a statistical likelihood. We are seeing events that are exhibiting stiction type characteristics, and we start to analyze that and metricize it. Once the likelihood starts to become significant, above 30–40%, we can say, and you can see on the top chart there, the likelihood is quite consistent across the range. You can come to some stiction charts and there's going to be very small sections of black line on them. Then you start to consider the amount. In the highlighted section there, we see it's 4%. So there's a 41% likelihood of a 4% stiction. It means that there's that strong correlation that there's a significant amount. We've lost 4% of control during that. You can see over there on that right hand side. But more importantly, there's specific periods throughout this time period that we're looking at here is showing amounts of stiction that you are significant, I suppose. There are some that are quite excessive and there are some that are small, but this period where you see the slider bar in the top right corner, if you look across, there's at least 4 different instances of this same type of or amount of stiction. So quite clearly you can say, okay, we do have significant stiction. Looking at oscillations, set point changes, this system is working to try and maintain and control on this. But to say we do definitely have a stiction problem here, or a stiction event scenario. Yes, our tuning suggestions directly below that are variants as well, but we have a mechanical problem here. George?
Right. I mean, I think this is really the key point here, to have a software system like Plant ESP tracking the performance of the valves 24/7 and identifying when that problem creeps in is so important. So because you just won't have time to go look at all the trends in your plant every day and try to pick apart what's happening and whether it's stiction or whether it's tuning or whether it's this or that. Having software do that for you is an ideal solution, because now it will only draw your attention to that valve when it knows that there's a problem. There's something to look after here. And so, and the 2 key points here, probability and severity, are really critical as well, because you can have, let's say, a very high probability that there's stiction, but it's only a little amount. Well, then you can kind of ignore it unless it's a critical loop. Or you can have a situation where we're not really certain, but we have a very high severity, a very large swing in the output. And so you can kind of put those 2 together and figure out what you need to do. On this slide, I think one of the most important things to take away from this webinar is the chart on the right-hand side here. What does stiction look like when we look at it closely? Now, this is in a fast responding loop, something like a flow loop or liquid pressure loop or something like that. You will see this pattern if a valve has stiction. You will see the process variable, the one on the top, moving in what looks kind of like a square wave. So it has kind of a flat top, and then a sudden movement, and then a flat bottom, and then a sudden movement and a flat top, and it'll cycle back and forth and back and forth. Maybe not quite as perfectly regularly as you see this one here, but in that same square wave kind of pattern. And on the bottom, you see what the controller output looks like in a typical PI or PID loop when you have stiction. The controller output moves in what some might call a triangular wave. I tend to think of this one as like a shark fin. It looks like a shark's fin, a wave going up and down and back and forth. And so when you see
sawtooth is another one that is
sawtooth, yeah, sawtooth is another way people describe that. Square wave, sawtooth, square wave, shark fin kind of pattern. That's a pretty good indication that what you're seeing is actually stiction and not tuning. Because if you think about that, what does a tuning problem look like? A tuning problem tends to look like, if it's over-tuned, if you have too much gain or too much integral action, it tends to look like pure sine waves for both the process variable and the controller output. But this one very clearly is not that. This one very clearly is illustrating that there's stiction on this particular valve. So I suggest you kind of keep that pattern in your mind if you think that stiction might be a factor, or if you dig into an oscillation and you see this pattern, what should immediately come to mind is, we might be dealing with stiction here.
Yes, indeed.
But next slide, please. So why detect it early? You know, why do we try to find it early? Why not just let it go until somebody complains about it, or an operator sees a problem? And the reasons are many, as you see on this slide. First and foremost, at the top of the slide over there, increasing the valve life. Well, if you think about what's happening here, that valve is cycling, is slipping and popping and slipping and popping and slipping and popping hundreds of times per day. I have literally been in plants where you can look physically at the valve and see a shiny part on the center of the stem of the valve from where it's been operating up and down and up and down and up and down and up and down all the time. You're wearing that valve, and if that's what it's doing to the stem, imagine what's happening to the seats on that valve. You're wearing that valve much too rapidly, wearing it out, and leading it to need to be repaired or replaced much sooner than it would otherwise be. Of course, if the valve is moving, it's affecting the process. And so all of these other things on the chart here are being affected as well. If you have if you have stiction on, let's say, a fuel flow valve, for sure it's impacting your energy efficiency, right? Anytime we think about that, I use a lot of analogies of cars, but imagine if you stepped on the accelerator on the car a little bit, and then you let off a little bit, and you stepped on it a little bit, and you let off it a little bit, stepped on and off. Yeah, sure, ultimately you might average the same position on the gas pedal, but do you think that was the most efficient way to drive, with your foot going on and off the gas pedal, on and off the gas pedal? Of course not. You're losing energy efficiency every time you speed up and slow down, you accelerate and decelerate the car. The exact same thing is true of your process, although it's a little harder to measure, but the exact same thing is true. It affects energy and quality and production and uptime and so on throughout the process. The impact of this kind of oscillation, this kind of cycling, is that it's hurting your plant, whether you know it or not. It's hurting your plant every day.
Yeah, the oscillation is key to that. It's something that people take for granted, particularly with new plant, new equipment. That these valves have 1 million cycles in them. We can run these, but it's the wear and tear that you build up in that first 18 months of perfect operation are going to start showing up further down the road, through aggressive tunings, through lack of maintenance. We just spent X millions on this plant. We're not going to have our maintenance budget, stressed for the first phase of this. All of these things will feed down the road into that process. We're perhaps exaggerating a little bit here, but there is those kind of scenarios that come with it. That the actions that are carried out on those early months and years of operation will either come back to bite you in the subsequent time, or you will, if you reap what you sow, if you have conservative.
You could be living with that loss, right, for days, weeks, months, years, without ever knowing what was causing that loss. And
yes.
The longer you let it go, the more you've lost. And so that kind of leads us to the next question about what to do about it. And I think, Damon, you've got a case study.
There's another case study here on it. So here's an example of a set of loops that were oscillating. Now we can see that and you can see the significant amount of stiction in those likelihoods and amounts. In the yellow there is that they're the amounts of stiction, but the system here wasn't picking them up because the process was not causing trouble, I suppose. But when we started to look at the interaction between processes, we could see that the stiction here was causing oscillation in other systems, and that was causing this widespread oscillation. You see on the frequency chart below, all those blue lines in the lower section, they are all of those loops that were oscillating at that same frequency. And this was the trigger to get us into this, for this customer to see, we need to do something about this because it was causing all of these oscillations. And you even look there, you know, there's 4 or 5 on that, you know, 3, 5, 7, 6% stiction. They are significant amounts. Now, maybe they weren't causing huge problems to the individual loop, but it was causing downstream oscillations is where this was caused, or it was sourced from. You know, as we worked back up the process, you could see these other loops that were causing it. Thankfully, the report there on stiction likelihood made that connection between correlation and the
But
frequency.
so often that's the case with oscillations. I mean, whether the oscillation comes from stiction or tuning or any number of other sources, the big problem with oscillations is that they spread, they propagate, right? They move throughout the plant. So if you start with a valve that has stiction, maybe even a relatively unimportant valve in the process, or a relatively unimportant control loop in the process, if it then induces oscillations in other more important controllers, it can wind up having a much bigger effect on the operation of your plant. So the big challenge with anything that causes oscillations is that oscillations spread, they propagate downstream in the plant, or, you know, God forbid, if you have some recycle or something, then you have kind of oscillations coming in on top of oscillations. It can be quite a challenging scenario. So getting to the root cause of that oscillation is so critical. And then once you've found it, to go ahead and investigate that valve and fix whatever the true cause of the oscillation may have been, whether it is an actuator that's too small, or an air supply problem, or the packing's too tight, or whatever those things happen to be that cause the stiction in that valve. That's really the ultimate solution. So,
Absolutely. Should have said before now, questions. I'm just curious, are there questions coming in? Just so feel free to type them into the chat there. We're well over, we're nearly 3/4 of the way through the session here. So if you have any questions, now's the time to get them onto the chat, so Vera can relay them over to us. Next
Perfect.
slide there, please, Vera. Thanks.
Yeah,
Vera.
we have one more poll here.
Okay, this is the sales pitch of it, just to say, do you want to know more about this process? We have the world of information. We have lots of case studies that we can share with you of applications where oscillation was attributed to tuning. And so by all means, please reach out to us. We can share the ones that we shared here as a minimum, but there's other specific ones. You may have a specific problem or question that we'll be able to feed into it. So by all means, our training classes are second to none from a practical understanding of it. We very much work on the process. We very much look to give you the information that will make you a good process optimizers, quite obviously using PID, but doing it practically. Any questions, Vera, coming in there? You want to throw one out while we're just finishing out that?
Sure. So let me start with one. What kind of tuning should I use if I have stiction?
Right. I love this question.
Yeah, it's go George. You go with it first, I suppose.
Well, this is one of those situations where we say, hey, take a minute, put on your safety shoes, and go look at the valve. Let's not talk about tuning and things we can do on the screen at the moment. If we have stiction, we should get up and we should go look at the valve. And I'm always surprised when I get to the valve about what could it be this time, right? It could be a tiny little actuator on a big valve. It could be, a small 1/4 inch air tube that's running 200 feet through the air supply. It could be, the packing is too tight. It could be that something's misaligned. It could be so many different things that you're always surprised, and you have to go look at the valve, right? The first thing to think about is not changing some numbers on the screen, but it should be going out and finding the actual root cause. So get on your hard hat, your safety glasses, your boots, and go take a look at the valve before we think about tuning. And then maybe you'll come back in a minute and I'll say a little bit about tuning, Damien. But
Yeah, indeed. As automation engineers, we have a terrible tendency to fix it with software. You know, I don't want to have to put on my safety boots and get out there on the plant. I'll just try and fix it with software. You know, but you know, you have to understand where this problem has come from. It's stiction, it's mechanical, it's physical. You know, you can tune the hell out of that loop. It's not going to change the amount of stiction that's there. It's going to, and in reality, if you try and make the valve work harder, you'll make the stiction worse. You know, is the reality of it. You know, because you know, you're just going to exacerbate the problem and force it. You may get a month, you may get a week, you might get an hour. You know, out of changing the tunings. But you know, I'm sure there's a question there. What tuning parameters should we use? I always say the first thing you should do is fix your loop. Fix your valve. You know, fix the mechanicals of it. Now, if you're in a shutdown is 3 weeks away or 3 years away, you have different consideration. George, what are your rules of thumb for a tuning adaptation to mitigate stiction? You will not remove it, but you may try and slow it down.
There are certain cases where you can do some things with tuning that would affect things. I'll take one of the most extreme cases. I've seen situations where if the stiction is due to sticky process fluid, right, where we know that the sticky process fluid is what's causing the problem, and that if we could only just kind of keep that valve moving regularly, that maybe that sticky fluid wouldn't build up on it and it might not lead to stiction. If I could just somehow keep that valve moving all the time, I might do that. And in fact, there were physical devices, electronic devices, and so on that used to do this, that we called dithering. You create this dithering process, which would just make the valve move just a little bit at a time and just keep it from staying in one position for too long. Now, as you can imagine, this creates some wear on the valve, but it prevents the stiction problem. And there is actually a poor man's way of trying to create dithering in our process. And you all probably know it certainly if you've been to the tuning classes offered by Control Station. How could we do something that keeps the valve moving constantly without a lot of difficulty? Well, there's an easy way to do that, and that is to put just a little bit of derivative action on the valve, on the controller, right? And so that will amplify any noise and just keep the valve jittering or dithering a little bit. Like I said, I don't recommend this in most cases, but there are those special kind of scenarios where it's the sticky process fluid that causes the problem. And if I could just keep the valve wiggling all the time, I can prevent the stiction problem from occurring. That's an opportunity to actually use tuning to solve a stiction problem. But I don't recommend that for the vast majority of cases. The vast majority of cases, you've got to go look at the valve.
You're not going to solve your process. You're not going to get your process back on set point. The best you can hope for is if you've got 1% stiction or 2% stiction. If you've got 2% stiction, double your integral. You're trying to slow the process down so that you are still going to be hunting, but rather than hunting at a 3-minute frequency, you'll be hunting at a 6-minute frequency. So you just lengthen out the process. It is still going to hunt until you get it or you limp it to your shutdown, to the end of the batch, it depends on how far away that opportunity to resolve is, I suppose. But you know, a rough rule of thumb is for every % of stiction, double your integral, you know, to slow it down, depending on whether you're above or below the line. Well, you know, you want to slow down the integral response by a factor of 2, I suppose, you know, for every %. Any other questions?
Yeah, we have 3 other more here. So is there any workaround of the stiction in the control size if mechanical fix is not applicable in the field?
Yeah, that's kind of that one, I suppose. You know, as George said, for the stickiness, but also if you slow the PID's response down, you're going to slow the frequency of oscillation, but you're not going to slow the size of oscillation, is the reality. It's going to go from a quick frequency to a much longer frequency is really the reality of it. George, would you agree with that?
I've seen is there are some positioner vendors, smart positioner vendors that claim that their positioners will have an algorithm that will accommodate or account for some of the stiction and give the valve a little extra boost each time that you try to get the valve to move to try to overcome that stiction in the short term. So that's something that you can look at as well if it's a feature of the positioner that you happen to have already, for example, or if that's something that you may be interested in. But I much prefer to fix the root cause than to keep slapping band-aids on top, but that is another possible solution.
How do you fix stiction? You go out, you don't tune it out of it, you go and you fix the mechanical problems, you know, that's the solution, you know, root cause, you know, is what you, but there is as we mentioned, there's ways to mitigate it to get you to that time where you can root cause it.
The other one is, can the vendors do more to prevent stiction?
Oh, that's a hard one, you know. So well, what I would say is, you know, we as automation, as process engineers, should do more to prevent stiction. You know, first of all, vendors have provided very expensive, very capable valves and pieces of equipment that have warranties and guarantees and reliabilities built into them. You know, so they've done a lot to do that. We have to be respectful of that. You know, because you know, a vendor says it has 1 million cycles on the valve. 1 million cycles sounds like a lot, but if you're constantly oscillating that valve because you're overly aggressively tuned the process, or you're constantly letting the packing dry out because of the environment that you're operating in, you know, you're making it hard for the to be successful, I suppose. You know, the vendors have certainly tried to give you the best capable piece of equipment. They have hazardous environment setups, you know, and all of those things, but it's not always possible when we get to it as operators, as process control people, you know, to go, we should have used a, you know, a different material, a different packing in this valve, etc., etc. It's not always possible. George, what's your thoughts on that?
I would try to, rather than to put too much focus on the valve vendors themselves, I think more focus in the engineering design phase is where you can mitigate stiction. You know, making it be a design criteria that you choose actuators and positioners appropriately. You know, there are some, I don't know, 100 to 200 decisions that go into selecting every single control valve that you have, and putting some emphasis in that part of the process on not only do I have the right size piece of equipment, but also how will it perform dynamically? Is it going to be capable of performing without stiction? Is it going to be capable of smooth operation throughout its range of control? And asking those questions at design time are really where, if I were to put more emphasis in at the beginning of the process, that's where I would put it. Make sure I've got an actuator that's big enough, make sure I've got an air supply that's big enough, make sure that I've thought through the selection of valve seat materials, for example, for how that's going to impact stiction as it relates to the type of process fluid going through there. Make sure I've thought about corrosion resistance. Is it worth a little bit more money for more expensive metal that'll be a little more corrosion resistant to avoid a stiction problem down the road? I mean, those kind of considerations, I think, are key in the upfront design of the plant, or in the selection of a replacement valve, if you should get to that point.
Yeah, absolutely.
Thank you.
Yeah, thanks, Vera. Sorry, just
you go.
No, you go ahead.
No, I just want to say, because Thales here said the QR code for the next webinar is Crush. So I put on the chat the link, then you can go directly to the link, or in our website, controlstation.com, there is a tab named Events, and then Public Webinar. You can find it there too. And I'm sorry about it. It's something about the platform. But you go, Damien. Do you want to add some?
I was just going to mention the webinar again. So that's perfect.
Okay, we have one more question. So I think we have time. We have six minutes. So You are about the software for Stiction's remediation. Do you suggest which brand of pneumatic positioners that have zero air bleed for sustainability, or monitor an alarm on Stiction becoming too much based on amount of time to open close? Don't know if you get it. I can read it again if you want.
Well, George, what are your thoughts? You know, I don't have a huge expertise in the vendor supply of those type of valves, etc. You know, so what I
The
would say
answer is
is,
going to depend quite a bit on, you know, what type of valve do you have? Where is it? Is it sliding stem or rotating valve? Which vendor's valve is it? You know, we generally look at that as well in terms of compatibility and so on. So very hard question to give a blanket answer to. Just too many different design factors involved there.
yes, perhaps my experience is, you know, the more modern plants are certainly have come a long way in and vendors have provided a lot more capability with them. You know, it's a kind of a get out or a cop out response. You know that, you know, the more modern plants have certainly got more flexibility on that. But you know, as George you said, to get involved in the spec, you may be heavily involved in project design, or maybe you're heavily involved in operations, but feeding that back in, if you're an operations person, feeding back those experiences on this product in this plant caused these problems for the next iteration, you know, that learning and feeding that information back in will be key to it. But it's kind of a cop out on the question, I suppose.
Yeah, I mean, the one added advantage of the modern smart positioners is not only do you get a little more ability to tweak and adjust, but you also get more information being captured that can be further analyzed later. So that's kind of the big improvement there in terms of whether it actually improves Stiction or not. I think again, this is going to depend a lot on the specifics of that issue.
A lot of those vendors have now got edge IO, you know, so that you're bringing a lot more information back from those controllers across their own networks, you know, to be able to make good decisions and to make good maintenance actions from it. Indeed.
Good.
Okay, I think thank you for your time. It's been a good conversation. Any questions? Feel free to reach out. Barrett had given the list of the various different points of contacts. Your survey questions will be, you know, if anybody requested information or follow-ups, we will certainly get those. There's some of our regional reps. Feel free to screenshot, take a picture, go to our website, and you'll get the details of those to follow up with them, I suppose. You saw myself and George's name. We're on LinkedIn. By all means, reach out, connect, you know, and
Absolutely.
what I say is I promise you I won't respond within 30 minutes or an hour of a question, but I will do my level best within 24 to 48 hours. So don't email me a question that you need the answer for now, but by all means feel free to reach out to pass something by me.
Thank you very much, and I hope you have a lovely week. Thank you, George and Damon. It was great.
Thank you, Bear. Thanks, Dean. Thanks, everyone.
Bye. See ya. Bye-bye.